Sir, good morning, sir.
Hello.
Good morning, sir. Okay, sir.
Okay, fine. ஒரே நிமிஷம் ஒரு ஃபோன் கால் மட்டும் அட்டெண்ட் பண்றேன்.
Okay, sir. Okay. 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 Thank you. Thank you. Sir.
மோஸ்ட்லி கெமிஸ்ட்ரி ரிலேட்டடா இருக்கும், பரவாயில்லையா?
பரவாயில்லைங்க சார்.
ஸ்ட்ரக்சரல் கேரக்டரைசேஷன் தான்.
சரிங்க சார்.
அதான் பேசிருங்க. வெயிட் பண்ணுமா?
Yes, sir. So 3 days, yes, online cycle job. Hello, Professor. Good afternoon.
Sir. Good afternoon, sir. Good afternoon. Sir.
Welcome for the program.
Thank you,
And
sir.
thank you for your participation, active participation in this work. I take this opportunity to welcome all the participants for this 3 days faculty development program on spectroscopic tools. We are having 3 great resource persons. First day, we have Dr. R. Rajit Kumar, Assistant Professor, Department of Organic Chemistry, that is School of Chemistry of Madurai Kamaraj University, Madurai. And for the second day, we have Dr. P. Tamilarasan, Scientist and ACSIR, Assistant Professor, Electronics and Electrocatalysis Division, CSIR, Karaikudi. And for the third day, we have Dr. S. Ramalingam, Assistant Professor of Physics, ABC College, Mandam Bandal, Mayiladuthurai, Nagai District, Tamil Nadu. I take this opportunity to welcome all the participants for this 3 days FDP program. And I have the job of introducing the resource person of today, Dr. R. Rajit Kumar. He belongs to Nilgiris, and he has completed his BSc and MSc Chemistry in Government Arts College, Ooty of Bharatiyar University. And he has completed his PhD in Chemistry in Madurai Kamaraj University at 2008. He has completed his postdoctoral fellow under Professor Henry B. Kagan, University of Paris, France. And he is a visiting scientist for Madrid, Spain. And he is right now the Assistant Professor of Organic Chemistry in Madurai Kamaraj University. 9 of his students have been awarded with PhD, and one of his scholars has submitted his thesis, and 5 research scholars are doing their work under him. And he is having 63 publications in peer-reviewed journals with a cumulative impact factor of 176.6, and with 1,275 total citations till date. And he has presented papers, 41 papers in conferences in both in national and international level. And he has organized one seminar funded by DST New Delhi. And he has completed 2 major research projects, that is from DST and UGC. And a few awards that he got. He's a postdoctoral, he got the CNRS postdoctoral fellowship Paris by 2008 and 2009. And he was awarded with the DST Young Scientist Award, New Delhi in 2009-10. And the Citation Award in Appreciation of Remarkable Research Contribution during January 2016 to July 2017 by Madurai Kamaraj University, Madurai. And he is active reviewer of ACS, RSC, Elsewhere, Willy, Theme, Taylor and Francis, Bentham Science, Springer, etc. And he is a life member of Chemical Research Society of India, National Magnetic Resonance Society of India, and he is a member of Board of Studies of School of Chemistry and Board of Studies in Chemistry, Saurashtra College, VHSN College, Lido College. The list is running pages to pages. And he has given several lectures in various colleges, and he is a IPSC member of Madurai Kamaraj University, NIR of Core Working Committee member, Project Implementation Group member, Exam Coordinator for School of Chemistry, in charge of Yan Williland scheme in the MKU, and in charge of 300 megahertz NMR spectrometer of School of Chemistry MKU, and a spectrofluorometer Central Instrumentation Center MKU. And above all, he is a great teacher, and for the past 10 plus years, he is working as assistant professor in Madurai Kamaraj University. With his expertise in this topic in the instrumentation, spectroscopy instrumentation, I hope that the participants, after having a very good lunch and having a supposed to have a little nap, we are supposed to be alert in this, because I think that Rajit Kumar sir will bombard you with all the techniques he is exposed with. So, dear participants, be please ahead and along with us so that we can have an exposure of all the instrumentations involved in the spectroscopy. Thank you. Once again, I will take the opportunity of welcoming our resource person, Dr. Rajit Kumar. Welcome you, sir, of Jamal Muhammad College. And dear participants, be with us for the 3 years and enjoy all the information and have it so that you can have an exposure of all the techniques involved in spectroscopy. Good luck and thank you. Welcome, sir. And it's your time.
Thank you, sir. Thank you very much for your kind words.
Thank you.
So, let me share my screen. Share ஆகுதுங்களா?
No, sir. Not visible, sir.
இப்போ பாருங்க.
Yes, sir. Visible, sir. Now it's okay, sir.
Okay.
Oh, okay, sir.
Very good evening to one and all. I think I'm hearing my echo.
Yes, sir.
Someone has, I think, unmuted. Hello.
Yes, sir.
கேக்குதுங்களா?
Oh, okay, sir. Now we are audible, sir.
இல்ல அங்க நீங்க உங்க சவுண்ட் கம்மி பண்ணுங்க, எனக்கு எக்கோ அடிக்குது.
Orange. Sir, இப்போ பாருங்க sir. இப்போ okay sir.
Okay.
Okay, sir.
Thank you.
Okay, sir.
Thank you, organizers, for inviting me to give a lecture in NMR Spectroscopy. So mine will be almost kind of chemistry related. So if you are synthesizing any new compound, then how to characterize it using 1 and 2-dimensional NMR spectroscopy. So that is going to be my topic. Now, this is a brief history of the development of NMR spectroscopy right from the 1943 onwards. So various stages, several Nobel Prize were given, and mostly the main scientist was Richard R. Ernst, who developed the Fourier transform NMR and the 2-dimensional NMR technique. And then came Kurt Woodrich, who used NMR for structuralization of protein molecules. So later on in 2003, two scientists, they got Nobel Prize for the magnetic resonance imaging. So it's a gradual development of the instrument. And when you go for compound characterization methods, so once you are making something new in the lab, or you are isolating from the natural resources, and you expect the compound to be active against some disease or so. So you are having it, but how to characterize it? You need to know what the compound is. So directly going to spectroscopy is not advisable. Before that, you need to do initial characterizations. That is, you need to know what it has. Like The elemental analysis will give you the composition. So what kind of elements are there in the compound, from there which you can generate the molecular formula. So getting molecular formula is the first and foremost characterization. And then GCMS will help you, and HR mass also will help you to identify the molecular formula. So once you do that, once you got the molecular formula, then you can go for the spectroscopic techniques to identify what kind of compound it is. Now, spectroscopy, there are several techniques, if you know it very well. IR spectroscopy deals with the vibrations of the bonds. So this technique will help, will be helpful to identify the functional group present in the molecule. UV will not help you directly in illustrating the structure, but it has its own applications. You can find out the lambda max, you can find out the conjugation, etc. So this deals, deals with the electronic excitations, the compound. And then the NMR it deals with the nuclear spin of the certain kind of nucleus. And this technique will be very much helpful to identify the structure and also stereochemistry in most cases. And finally, you have the X-ray diffraction. X-ray, if you're lucky enough that if your compound you are able to grow single crystal, then you can use this technique, which gives you the three-dimensional picture of the compound. It's an ultimate technique, but it is very difficult to grow crystals. Keeping the nature of the compound in mind. So NMR will give you almost all the information about the structure. Now, what is NMR, nuclear magnetic spectrum? So it is a phenomenon which occurs when the nuclei of certain atoms are immersed in a static magnetic field and exposed to a secondary oscillating field. Now, when I say certain nuclei, not all nuclei are NMR active. So something deals with the nuclear spin. So only certain, only the nucleus which have the nuclear spin, they are NMR active. It is the subatomic, fundamental property of subatomic particles. So not all kinds of all the atoms are having spin. Depends on the number of neutrons and number of protons. So if they are both even, these kinds of nuclei will not spin, will not have the I value, and hence these kinds of nuclei will be NMR inactive. So you can't record NMR for this. And when the number of neutrons plus the number of protons is odd, then these kinds of atoms will have half integer spins like 1 by 2, 3 by 2, 5 by 2. So in organic chemistry, mostly you have proton, carbon, nitrogen, fluorine, silicon. Silicon is less common, but phosphorus, these kinds of nuclei, all these nuclei have spin value of half. If both the neutrons and number of protons are odd, then you have whole number, the integer spins like deuterium N14, you have I value 1. So certain nuclei has spin, or you can say has I value. So what? Then any spinning nucleus will exhibit magnetic properties. That is, it will behave like a tiny magnet. So like our Earth's magnetic field, so the induced field is parallel to the spinning axis. And these nucleus can be shown as tiny magnet, and with the magnetic moment being given as gamma I into h. Gamma is the barometric ratio, I is the spin, and h is the Planck's constant. And you can see that when I is 0, there won't be any magnetic moment for such nuclei. Then, so when these kinds of these spinning nuclei, they are placed in an external strong magnetic field, what happens? So firstly, the strong magnet, the B0, will tend to align the nucleus along with itself, and the spinning of the nucleus will make that the nucleus wobble. It's like a spinning top when it is about to fall due to the gravitational pull. You have a circular motion along with the spin. You have another circular motion. So that these two are very important, and that wobbling is known as the precession or the precession frequency, which is given by the equation mu equal to gamma B0 by 2 pi. Now, it not only precises, but it also takes certain number of orientations depending on the I value. So that is given by 2i plus 1. So when you take a half spin nucleus, it has two quantized energy states, you can say. So one is the alpha state and the other is the beta state. So once you place a spin half nucleus in an external magnetic field, it can either align with the nucleus, external magnetic field, or in the oppose the external magnetic field, which is the ground state and the excited state, respectively. And according to based on the spin value, we have that many number of orientations for different kinds of nuclei. But remember, whenever the allowed transitions are across unit difference, that is, it can flip through only unit change. Now, when you take all the spin half nucleus, as I told you, it can either align with the external magnetic field, or it can oppose the external magnetic field. So one is the alpha state and the beta state. So nuclear spin, and then once you place that spin in external magnetic field, it can take that many number of orientations along with the precision frequency. Now you can see that a degenerate state, so there's no B0. So all the spins are differently oriented. And once you place that in an external magnetic field, you have that many number of orientations. In this case, it is plus half and minus half. The energy gap between these two quantized states, it's given by the precision frequency. That is, if that here you can see that gamma B0 by 2 pi, all are constant except B0. B0 you can change, but other things you cannot change. So if you want to have a large energy gap, then you need to increase the B0. And when you have millions of nucleus, maybe in 5 milligram of compound, so at B0 is 0, all the spins are randomly oriented, and totally the energy is 0. And once you place it in an external magnetic field, then there is highly orientations. So according to the I value, that many number of energy states are, split into energy states. And in the case of spin half, it is plus half and minus half, or you can say alpha and beta. How many nucleus will occupy in the ground state and how many in the excited state? That is given by the Boltzmann distribution. So the Boltzmann distribution says that the population is almost 50% with small excess in the ground state. So only that small excess is responsible for the NMR spectroscopy. So you can say that NMR is a very sensitive technique. If you have 2 million nuclei, you can say that in a 300 megahertz instrument, you just have only 48 nuclei excess in the ground state. So it's very sensitive. Now, once you attain the Boltzmann equilibrium, once you place your sample in an external magnetic field, then this Boltzmann distribution is attained. So once this Boltzmann distribution is attained, you need to disturb the population so that there is some energy absorption or emission takes place. To do that, an external radio frequency is given perpendicular to the B0. So the energy gap between these two lies in the radio frequency region. It's a very weak energy. So it is given by an oscillating coil. So once the precision frequency of that nucleus matches with the radio frequency, the flipping takes place. The ground state nucleus, the nucleus in the ground state will be excited, absorbing the energy, and it can't stay in the ground state for a long time. It comes back, it relaxes, and it leaves the absorbed energy. That is recorded as the NMR signal. So relaxation process, you have longitudinal and transverse relaxations. So those things I'm not going to go into. And you have two different kinds of instrumentation. So one is the continuous wave and the other is the pulse technique. So continuous wave is not used nowadays. So it's like tuning your FM from one end to other end. Wherever there is matching, you get noise. So in that way, the magnetic field strength is kept constant and the radio frequency is swept from a small value to one value to another, so that wherever there is the matching of the radio frequency with the listening frequency of the nucleus, the signal, you get the signal. So that it has a lot of disadvantages. You need sample, and then for proton to record, it will take around 30 minutes. So that is not news now. Now the technique is the pulse technique or the Fourier transform technique, where there is a short pulse of burst of pulse given to the nucleus. So irrespective of what the different kinds of nucleus, all the nucleus will be excited at the same time. And based on the T1, the relaxation, So it has different time. The different nuclei have different time. So based on that, you have the pre-induction decay recorded, and then the this time domain spectra is then converted to the frequency domain spectra through the Fourier transform. So this is how you record the signal is recorded in the NMR. So in classical method, as I told you, this is the instrumentation, very old instrument, and this is the instrument which we have in the School of Chemistry now. And Bruker has gone up to 1.2 gigahertz NMR. The magnet will be huge. So this is the latest news. The Bruker has developed 1.2 gigahertz NMR. Now, that was a small kind of theory which I wanted to rush very fastly. Now, next, you need to know some certain important concepts in NMR so that it will be helpful in structural illustration. So we are going to see proton and carbon NMR, the number of signals. So once you have been given a compound or a structure, you need to know how many proton signals and how many carbon signals that compound will give. So that depends on the proton in different chemical environment will need different frequency. For example, if you have ethanol, you have CH3, CH2, and OH. So CH3 is one kind of proton, CH2 is a different one, and OH is a different one. So you have three signals in the proton NMR. So similarly in carbon, so just you now count the number of carbons, that many number of signals you will get in the carbon NMR. And then the second important concept is the position of the signal, or you can say the chemical signal. So where it appears. So how many number of signals the compound will give? Number one. Number two, where it appears, and that we'll see a little bit later. And number three is the spin-spin coupling. So the nucleus, the spin, that is, if you have different kinds of nucleus, for example, CH3, CH2OH, as I told you in ethanol. So that CH3 will not give one signal, but it will be split based on the number of neighboring nucleus. So that also we are going to see a little bit later. And there are different kinds of splitting, geminal, vicinal, and long range. In carbon, you need not worry about the coupling because you are completely decoupling the proton. And the intensity also will give you some informations, which we'll show it in an example a little bit later. So, predicting the number of signals. A few examples we can see. As I told you, ethanol, the CH3 is one kind, the CH2 is another kind, OH is another kind. So, totally, you will get three signals in the proton. And in carbon, you have only two carbons, CH3 and CH2 carbon. So, you will get two. So similarly, you have other examples. You can see here 1, 2, 3 proton signals and 3 carbon signal. And again, you have 1, 2, 3 kinds of protons, different kinds of protons, and then one carbonyl carbon. So you will get 3 in carbon, proton, and 4 in carbon. And similarly, you have other examples which I will just show. Now here you can see you have a tertiary butyl group, so which you can think like the CH3 is near to chlorine, so that all the this methyl is different from that methyl. That's not the case because you know very well that the CC bond is rotating very fastly, so that all these three tertiary butyl methyl groups will be giving only one signal in the proton NMR. So wherever you have a tertiary butyl group, you can expect only one signal for that. All the three kinds of protons and also carbon as well. So you will get 1, 2, and 3 in the proton and 4 in the carbon, including this ipso carbon. And when the compound is symmetry, then the number of signals will reduce. So there are 1, 2, 3 CH2 groups, but the CH2 attached to the two bromine, they are in the same chemical environment. So you will get only one signal for this. So you will get only 2 in the carbon and 2 in the proton NMR. So once you have a symmetry, the number of signals will reduce. Again, another example for the symmetry. Here you have an isopropyl group. Again, similar to the t-butyl group, the isopropyl methyl groups are same. So you will get only one signal for the 2 methyl groups, and in fact another for the CH. So 2 in the proton and 3 in the carbon. Benzene. So you have C6 and H6, but you have CN axis of symmetry for this compound. So whatever compound you have a CN axis of symmetry, you will get only one signal for those types of compounds. So any compound it may be, you will get only one signal. And cyclohexane, we know that it has a chair conformation. So at normal room temperature, you will get only one signal in both proton and carbon. But when you reduce the temperature to about minus 90 degree, the flipping is arrested, and all the axial protons will be giving one signal, and all the equatorial protons will be giving another signal. So you will get only, you will get two signals at low temperature. And benzene, we have substituted benzene. It's a monosubstituted phenyl ring. So when you have a monosubstituted phenyl ring, the ortho protons will be giving one signal, meta, and then the para. So you get three signals if you have a monosubstituted phenyl ring. So toluene, you can see that it should be giving four, but gives only two because this methyl group is not influencing electronically inside the ring, so that all the proton and carbon will feel the same electron density, so that you will get only two signal in the proton and but five in the carbon. So these are some other examples which I will just or similar examples. And second is the position of the signals. That is the chemical shift. This is an important concept here. Now we know that you have three different kinds for kind of protons in the case of ethanol: CH3, CH2, and OH. So you can see that the electron density around the protons will be different. So the chemical shift completely depends on electron density. So once you have more electron density on a nucleus, it means that it is shielded. And if you have lesser, then it is deshielded. So this electrons, they always oppose the external magnetic field. So it is kind of shield the nucleus. Now, we know that the frequency, the special frequency is gamma B0 by 2 pi. So at what frequency the nucleus should resonance, or resonate? It depends on the magnitude of the applied magnetic field B0 and the gravimetric ratio. You know that both are almost constant. And the third one is the chemical environment of the nucleus. As I told you, if you take ethanol, you have CH3, which is more electron rich when compared to CH2 and when compared to this OH. So you have different crystal frequencies, or you can say that when you place this ethanol in a 300 megahertz external magnetic field, then you expect all these nucleus to precess at 300 megahertz, but it won't. So it will have a very small difference in the crystal frequency. Maybe this OH proton will precess very fastly when compared to the other two, because it is less electron dense. So you have a small change, a minor change in the crystal frequencies for each of this these types of protons. So that field independent shielding factor is given by sigma, that you have to reduce minus from the original B0. So your B actual felt by the nucleus will be B0 minus B0 into sigma. So which you can write, simplify as 1 minus sigma. So it will be different. So when in a megahertz scale, in a 300 megahertz scale, you have minor changes, or you can say in a hertz, the changes between the methyl proton and the CH2 is in hertz. So our aim is to directly measure the exact crystal frequency of the nucleus. So that is not possible. So for that reason, the internal standards was introduced. Because when if you take, for example, if you take acetone, then at 60 megahertz, if you record the NMR, proton NMR at 60 megahertz, it will precess at 120 hertz. And when same acetone, when you take it to 100 megahertz instrument, it will precess at 200 hertz. So you will have two different values for same compound. So that is not good. So wherever you record the NMR, it should be standard. It should be giving the same value. So for that, tetramethylsilane was kept as the standard, internal standard, and the frequency of the nucleus which you are recording. So at what distance it appears from the TMS, that is called as the chemical shift, so which is given by the frequency of the substrate or the substance minus the frequency of the TMS divided by the instrument field strength. So once you have this hertz per megahertz, the unit is parts per million. So wherever you go, wherever even if you take it in record in 1,000 megahertz, the acetone will have the same chemical shift value of around 2.1 ppm. Now, if you take proton NMR chemical shift, the scale is very narrow. So maximum all kinds of protons will appear between 0 to 10 ppm or maximum up to 9 ppm. And beyond that, only less number of protons will be giving signal. So it's very narrow, and there are chance for overlapping signals also. And once you take the scale, it is the TMS is kept at 0, and your signal appears at which position, that depends on the electron density. Now, the signals appearing near to TMS is called as shielded protons. That means that the electron density around the nucleus, around the proton, is more when compared to the de-shielded protons, or you can say upfield and downfield. So when you take carbon NMR chemical shift, it's very wide. So you can say it can go up to 250 ppm. And similarly, the shielding and de-shielding also is the same in this case in proton also. So this is the approximate chemical shift values of different kinds of protons. So you can find it in several books and also in the internet resources. And you can see here the carboxylic acid proton, they appear at around 11 or 12 ppm, and the aldehyde proton, they are de-shielded, whereas the alkane protons appear near the TMS. And above 6 to 8 or 9, you can say that all the benzene ring, phenyl ring protons will appear, will give signal in that zone. And if you take carbon, the highly de-shielded carbon will be the ketones, the three ketones, and then aldehyde, amide, and all such kinds of carbon will give will appear at around 170 to 220 ppm, and the alkanes and heavy atom effect. You can see that when iodine is attached, it is highly shielded when compared to chlorine or bromine or so. So it all depends on the electron density. So if you have more electron density, then the signal will be towards TMS. And gradually, if you get signal away from TMS, that means the electron density is less. And the third concept is the spin-spin coupling. I told you we expected 3 signals in the proton NMR for ethanol, and for some other compounds also we predicted the number of signals. But as I told you, it will not appear as a single line, but it will split accordingly based on the number of neighboring nucleus. So that is given by 2n I plus 1. So if you are trying to predict the splitting pattern of a particular proton, so you can apply this 2n I plus 1 rule to get the number of splitting pattern. For spin half nucleus, you can just write n plus 1, number of neighboring protons plus 1. Now, we discussed that there are different kinds of coupling. So one is the geminal coupling. Geminal coupling, in the sense, the distance between the two coupling nuclei is the number of bonds are 2. That is, if protons are attached to same carbon, and when these two nuclei they couple, they are called the geminal coupling, which is very strong. Vicinal, if a proton attached to one carbon is coupling to the proton attached to the neighboring carbon. So that means that you have 1, 2, 3 bond distance. And those kinds of coupling are called vicinal, which is a little bit lesser than the geminal. And long range, if you have more than 3 bonds distance, then those kinds of coupling they are called long range. So the coupling can be measured using the J, that is the coupling constant. So that will give you the magnitude of the coupling. And the J decreases with the increasing number of intervening bonds. Now, how or why the splitting takes place? I'll show you the example. And when you have only one nucleus, it means obviously it won't. There's no nearby coupling partner, so you will get only one line. That is one spin. That is it is in the ground state. So it gives only one line, which is called the singlet. Now, once you have one coupled nuclei, so the red one is the coupling nuclei, and the blue one is what we are, predicting the splitting pattern. Now, when this blue proton should be in the ground state so that it can absorb the energy. But this red proton can be either in the ground state or in the excited state. So it can be in the two different states. So this one line is split into two lines now. One is away from TMS and one is towards TMS. That is, here you have both positive energy and here you have one positive and one negative. So you have two different lines. So that is called as the doublet. And similarly, if you have two neighbors, then the situation is a little bit complex. You have 1:2, 2:1 triplet. And if you have three neighbors, again, you have different combinations. You get a quartet, like 1:3, 3:1 quartet. And if you have four coupled nuclei, quintet, five coupled, you get a sextet, and six coupled, you get a septet. So as the splitting goes on, increasing, the lines at the end will be going along with the noise and you will not be able to see. And in those cases, you can just write multiplet. You are not able to exactly see the splitting pattern. Now, we'll just rush up with some examples which we predicted the number of signals. We'll try to find the splitting pattern. Here you can see that you have three protons which are same, and it has two neighboring protons, CH2 here. So obviously n+1, it should give a triplet. And this CH2, it has three neighboring protons, so it will give a quartet. And this OH protons, or you can say generally NH, OH, and all these heteroatom attached protons, they don't tend to couple because they are kind of exchangeable protons. So they don't sit in the same molecule for a long time for the NMR the NMR scale. So they always give broad peaks in the NMR, proton NMR. And you can see that this will be a triplet and this will be a quartet, and this OH will be broad singlet. And here CH3, you have two protons, so it will be a triplet. And this CH2 has 3 + 2, 5. So 5 + 1, sextet. And this CH2 will give you a triplet because of this neighboring CH2. And similarly, here this is isolated, so it will give a singlet and a quartet and a triplet. So wherever you have a quartet and a triplet, you can expect a CH2, CH3 group in the compound. And again, here you have a singlet. Both are singlets because there is no coupling partners, neighboring coupling partners. So here you can see this methyl group. It's a doublet because you have a CH here, and this CH has three neighboring, so it's a quartet. And all these three will give singlet because all are same. And here you can see, even if it is a symmetry, they are chemically different. They are magnetically same, but chemically different. So you get a quintet for this middle CH2 because of the two CH2s flanked near. And similarly, you have a septet and a doublet. It means that you have an isopropyl group with these two CH3 group coupling with the CH will give a doublet, and this will couple with 6 protons to give a septet. And the CN axis compounds will give only one signal, will be singlet. And when you take monosubstituted phenyl ring, you can say that this CH has one vicinal coupling, it will give a doublet, and the meta protons, it has two vicinal couplings, so it will give a triplet. This para proton also has two vicinal couplings, so it will give a triplet. So normally a monosubstituted phenyl ring will give doublet, triplet, and a triplet. So if you have a disubstituted phenyl ring, then all the protons will be different, so that you will get a doublet for this because of one vicinal coupling. Again, the extreme end, this will also give a doublet because you have only one vicinal coupling. But these two protons will be giving triplets because it has two vicinal couplings. And if you have 1,3 disubstituted phenyl ring, so this will give a singlet, and other three will be giving two doublets and a triplet. So I'll just this was the same kind of examples. Fine. Now we have seen three important concepts: the number of signals, the chemical shift, and the and the splitting pattern. And now we are going to see a little bit, interesting um, concept here, intensity of signals. Here you can see that you can integrate all the signals appearing in the proton NMR. And if you integrate one, the computer will automatically generate all the other integrations. And if you have your molecular formula in your hand, then you can directly say that by counting the number of the integration, you can say that that many number of protons are present in the compound. In this case here, all the signals are assigned. And the molecular formula is C17H15N3O, and the number of H is 15. If I count here, I can see that I can get 15. So the intensity will indirectly give you the number of protons present in the compound. So we have seen all the four concepts. Now I'll show some examples of the different 1D and 2D experiments of one particular compound, the ethyl benzene. So you can see this is the structure of ethyl benzene, and the CH3 will give a triplet. This will be giving a quadret, and the ortho protons will be giving doublet. The meta will give a triplet, and the para will give a triplet. So in proton you will get 5 signals, and carbon you will get six signals. You can see this is the proton NMR spectrum of this, the ethyl benzene, the triplet, the quadret, and you have some multiplet here. So the number of signals are 5. And of course, if you record in CDCl3, the signal at around 1.6 corresponds to the moisture present in the compound. And to report a chemical shift value, you need to get the midpoint of the signal, and that will be your chemical shift. And you have to say the splitting pattern, whether it's doublet, triplet, singlet, etc. And then you have to give the J value. J value is calculated by subtracting the two values and multiply by the instrument field strength. In this case, it's a 300 megahertz, so I get 7.5 hertz. And if I know, because of the exact chemical shift of that the nucleus or the type of nuclei, I can write that. Otherwise, it is not necessary. And this is a quadret, 2.66 quadret, J equal to 7.5 hertz. And this coupling is mutually, you will have mutual coupling. When you can say that these two are coupling partners just by looking at the similar J value. So, and if you are not able to exactly say the splitting pattern, then you can write the starting value and the end value, and you just write it as multiplet. And if you know the number of signals, you can write, otherwise you can just write this is because of phenyl ring protons. And this you know already. So this is the carbon NMR spectrum of this ethyl benzene. So there are 1, 2, 3, 4, 5, 6. Remember, all the 2 ortho and the 2 meta are same. So you have 1 methyl, CH2, 3 CH, and 1 ipso carbon. If I count the number of signals, 1, 2, 3, 4, 5, and the ipso carbon appears at around 145. So you have 6 signals. And in the middle, you will have 3 equal lines. So you can see here at around 77. So this NMR was recorded in CDCl3, and while recording the carbon NMR, proton is normally decoupled, but the deuterium is not decoupled. So for D, the I value for D is 1. So by writing the 2n I plus 1, you will get 3. So you will get 3 lines when you record carbon NMR in CDCl3. And then next technique is the depth technique. So it is called as the distortionless enhancement by polarization transfer. So in this these types of experiments, they won't give signals for quaternary carbon. So you can easily identify how many quaternary carbons are present in the compound. So here you can see that this is the normal carbon NMR in the inset here, but here you have at around 140 that is missing. So this technique is called the depth 145 NMR. So apart from the quaternary carbon, you will get signal for all the proton attached carbon, CH, CH2, and CH3. This is depth 45. In depth 90, as I told you, you can see here the signal is there, and it is absent in the 45. And second technique is the depth 90. In depth 90, very interestingly, you will get signal for CH only. So you can just run this NMR, this technique. It goes for around 20 minutes. You will just by counting the number of lines, you can say that many number of CH is present. So in our case, you have three different kinds of CH. You can see that the methyl and CH2 is almost suppressed and you cannot see the signal. So you'll have three signals in this case, in the case of depth 90 for ethyl benzene. And more interestingly, in depth 135, this is another technique which will allow you to identify the number of CH2 and CH3 present in the compound. So here you can see that the CH2 will be pointing downwards and the CH and CH3 will be pointing upwards. So it's making very much easy to for structural characterization. And once I record this depth 135, I can take my carbon NMR and I can overlap with the depth and I can mark which line, I mean, which signal is which, what kind of carbon. So I can see that here the CH3, I mean, this signal is CH3 and the second one is pointing negative. So this should be CH2 and the signal which is not there and which is there in the carbon NMR should be the ipso carbon. So just I can mark everything. Then the double irradiation. So double irradiation will be useful to identify the coupling partners in the proton NMR. So there's a 1D double irradiation. So you can see that here you have a triplet and a quadruplet. So this is the normal proton NMR. And I select this particular peak and I will give as a double second irradiation so that the signal pertaining to this proton will be absent here and the coupling partner, so whatever the nucleus is coupling with this nucleus, the signal will be disturbed. You can see that it was a quadret, now it is giving a singlet. So this technique will help you to identify the coupling partners, but it has its own disadvantage here because you can't go on doing this for each and every signals. So to overcome this, to bring all the coupling in one spectra, you have the COSY spectra. So now this is a 2D technique. You can say it's a 3D technique also. This you will have two frequency axes. And normally in proton NMR, you will have one frequency axis and the intensity in the other axis. But here you will have two frequency axes and the intensity will be coming towards us. So it's like cutting a tree and viewing from the top. You have the contours. So these are the contours. So once you go for 2D NMR, you can't say it's a signal or a peak, you say contour. So this is HH COSY spectrum, that is hydrogen correlation spectroscopy. COSY is nothing but correlation spectroscopy. Now once you record this, now how to find what all signals are coupling or the coupling partners. So once you record the HH COSY, you draw a diagonal line from the right corner, I mean top corner to the left bottom corner, and whatever the contours which are crossing this line will not give any information about the coupling partner, but the contours which are off diagonal, above and below the diagonal line will give you more information. So you can see here, once as I told you, this is the diagonal contours, and here you have one off diagonal contour for this triplet, and that corresponds to this methyl coupling with this CH2. And similarly, you have one off-diagonal contour for this quadruplet, and that corresponds to the CH2 coupling with the CH3. So once you join all these four lines, I mean four contours, you will get a square. So how many ever square you are forming, that many number of coupling are there present in the compound. So in another example, I will show you all the coupling partners. Here you can see that all the aromatic coupling have merged in a small chemical shift zone. Now this is another example will give you more information about the coupling. So you can see the diagonal, you can just draw the diagonal like this, and whatever the contours are that are crossing the diagonal will not give you any information, as I told you, and you need to hold the off diagonal. So I can draw one square here. So that means this signal at around 1 point something ppm is coupling with the signal at around say 2 ppm. It has one coupling here, and it has another coupling which is shown like this. So it has two second coupling at around 3.2 ppm. It has this nucleus is commonly coupling to these two, and there is another third coupling you can see. So this one particular nuclei, this particular proton has three couplings. So you have all the coupling in one spectra. So you need not do it again and again. And similarly, you can see here, you have the coupling partners like this. You can just by drawing lines, you can find out the coupling partners each and every for each and every signal. So this is the HH-CoC, and then the CH-CoC. CH-CoC is nothing but the coupling between carbon and proton. So which proton is attached to which carbon? So in the previous example, we had both axes. We had proton. In this case, you have one axis, you have proton, and the other axis, you have the carbon. So here we need not worry about the diagonal contours and other contours. Here just you draw two lines crossing the two axes. So that means that this triplet, this signal is attached to a carbon at around 14 or so. And similarly, we have the other signal also. And once you record the CH-CoC, you can just mark each and every signal taking the carbon NMR. Remember in depth, it helped to differentiate the kinds of carbon. And once you record the CH-CoC, then you can just write the chemical shift values, proton and the carbon. So for all the signals. And once you do this, now you need to, this is a simple compound. So you can say that only one methyl group is there and one CH2. So easily I can do it. Easily I can assign. If you have more number of methyl groups and CH2 and different kinds of as I told you, the methyl group and CH and the CH2, then this HMBC will help you to assign the exact chemical shift of each and every carbon. This heteronuclear multiple bond correlation, this is another interesting 2D technique. And here in one axis you have proton and the other axis you have the carbon. And again, this is the coupling between proton and carbon, but not one bond, but two bond and three bond. So if you take a system like this, so as shown here, so this proton directly coupling to this attached carbon is our CH-CoC, which we saw in the previous slide. But HMBC will give you coupling of this proton with the second and the third carbon. So 1-2 bond and a 3 bond distance. So this will help you to know the chemical shift value of the neighboring carbons. So not the attached carbon, but the neighboring carbons. So it makes very easy for the structural characterization. And here you can see that if you record how to approach it, I will tell you. Once you record the HMBC, you catch each and every signal and you draw a straight line like this. So you can see the number of contours which are crossing the line. So that will give you the information about the HMBC correlations. Now, if you take this, I know this triplet is because of this methyl. Now I can theoretically predict how many HMBC correlations these three protons will give. Now 1, 2 with the CH2 and 1, 2 and 3 with this ipso carbon, and not the fourth carbon. So it will give contours for 2 bond and 3 bond, not 4 bond. So I can see sometimes you will get contours like this, which you can neglect because this is nothing but CH-CoC. It's not crossing the line, so you can just omit it. And you can see here 1 and here 2. So that means the correlation of this methyl protons with the CH2 here and the ipso carbon. So what I can do is I can just pinpoint that this methyl group is because, this triplet is because of this methyl group, and the carbon is also assigned already. We have done it, but now we are fixing it to which, the chemical shift is fixed to all the different kinds of carbons and protons. And the CH2 I will know, and this ipso carbon also I will get the information. And if you take the second correlation of this CH2, so this two protons can couple with 1, 2, this methyl carbon, 1, 2 with this ipso carbon, and 1, 2, 3 with this ortho carbon and not the meta. So I can differentiate between the ortho and the meta. So once I know the carbon chemical shift, by looking at the CH-CoC, I can easily get the proton chemical shift. So 1, and this is again, you can omit it, 2 and 3. So you will have 3 different contours for this CH2. So you can't theoretically expect, you can experimentally, you can expect the number of predicted HMBC for each and every proton. So whatever you have got from that, you have to go back. And now I can see that an aromatic proton shows HMBC correlation with an aliphatic carbon. So that it must be because of this H, because this is the only H which is in 3 bond distance with the CH2 or the aliphatic carbon. So you can do it either way also. So this is about the HMBC, which will give you information about the neighboring carbons. And this is another technique which is less common, which is called the homonuclear J-resolved experiment. So this is nothing but the quartet, which was appearing as, you have this quartet here. So here, for overlapping signals or very closely overlapped signals, this technique will help you to get the J value. In this experiment, you have a chemical shift in one frequency axis, in one axis, and the other axis you will have the J value. So once you record this, what you have to do is, so this is the triplet. You can see 1, 2, 3. This is the triplet, and this is the quartet. 1, 2, 3, 4 is a quartet. So this is kind of rotating the signal to 90 degree and viewing from the top. So that's how the contours are here, and the midpoint is the chemical shift, and the distance between the two lines will be the J value. So if you are not able to identify the signal, the splitting pattern, then sometimes this J resolve will help you. So the distance between the two contours will be the J value. And this is another example for the J resolve. You can see this triplet, it is coming as 1, 2, 3, and the distance is 7.21 hertz. And you have very close overlap signals here. So that's why you can't find the J value. So that it is turned 90 degree, and viewing from top, you have 4 signals here, 4 contours here. So the J value is 7.21 hertz. So by this you can find out the J value. So these are less common experiments. And then finally, the NOSI technique. So NOSI will give you information. The stereochemical information you can get from the NOSI spectra. So don't worry about this reaction. So a compound has been made. It's a 6-membered compound, and they have recorded the proton NMR, and using all the techniques, the chemical shift have been assigned as shown here. And it's a 6-member ring, so the more stable conformation is the chair conformation. So all these two protons they come at around 3.37 and 3.73, and this CH it appears at 4.80, and the CH2 appears at 4.54 and 5.07 ppm. You need not worry about the assignment. So everything has been assigned. Now, in order to confirm or to identify the conformation, the 2D technique have been used here. You can see that this is the HH-CoC spectrum. So the diagonal contour, and you have all the coupling informations given here. And this is the NOSI spectrum of this compound. It looks similar to the HH-CoC, but apart from that, you will have different extra contours. So this corresponds to the HH-CoC, and apart from that, you have 4 different contours. So from that, how to identify? Now it means that the doublet at around 3.73 is spatially proximate to with a signal at 4.54. So these two protons are near to each other in space. So if you see here, 3.37 is the CH2, is one of the proton, is spatially proximate with 4.54. So at this, in this conformation, it is very difficult. It cannot, you cannot say that they are spatially proximate. No. And the second contour says that the 4.54, it's a reciprocal one. So 4.54 is near to 3.73. And another one, 4.80, is near to the phenyl ring proton. So this you can say, okay, fine, these two are same, near, but these two protons to be near in this conformation, it is not possible. So it was decided that the NOI correlations are given here. It was decided that the structure is not the chair form, but it's in a boat form. And these two protons are like, the flat pole interaction. So they are spatially proximate. So that's why you have this 3.37 and 4.54 near to each other. So this is another less common technique you can use for the stereochemistry. And the inadequate, this is another less common technique. Here, this will give information about the C13 coupling. It's very difficult. This kind of experiments will take, you have to run overnight for this technique to record this spectrum. So you can see that in one axis you have the carbon and the other axis you have the um, hertz. And if you're able to identify one carbon, then by going through the lines, you can say that they are coupling. You can identify the chemical structure of different carbons. So I know this one first carbon is attached to oxygen, so it should be highly deshielded, and this should be because of this first carbon. So this is 1,2 coupling here. So once you know one carbon, then this is the next carbon, and this is the third one, this is the fourth one, and you will have all the information coming from the coupling of C13 and C13, which is called as the inner equate. So, is it time now? Can I finish now? Hello?
Yes, sir. Yes, sir.
Yeah, I think we can finish it off now.
Okay, sir.
So, maybe I'll be able to answer some questions.
Sir, you can take another 5 minutes, sir.
Okay, then.
Okay, sir.
So I'll just discuss one example from our research group. So you can see how helpful this NMR technique is. So we did this reaction expecting this fused iron compound. So don't need, not worry about the mechanism and all. So we expected this compound, and we took all the NMR, and you can see that this is the proton NMR spectrum of this compound. It has one phenyl ring, and you have one, two, three, four, five CH2s and one CH. So, but unexpectedly, we got this is the expanded form. We got one triplet and a quadret. So it means that there is a CH2 CH3 group in the compound, which we did not expect. And also, you have a mono-substituted phenyl ring. So you have two doublets. And when you look at the expected product, it was, there's no chance for CH2, CH3, I mean, the triplet and the quartet in this expected structure. So, so we went for the HH CoC, and we saw that these two are coupling partners. There is a CH2 and CH3. We thought that there is some ethanol impurity, but that's not the case, and this is in the compound. So we went on further, and we took the carbon NMR. I'll come to this a little bit later. And in the depth technique, so depth technique, as I told you, can you'll get say CH2 in one side and CH and CH3 in the other side, and that depends on you. In this case, I've uh, made the CH2 to appear in the positive, and CH and CH3 to appear in the negative. So here you can see you have one CH3, CH2, there are 6 CH2s, and the CH, there are 2. So when we look at the expected product, it has only 5 CH2s, and there are no CH3. And CH, there are 3. So based on this also, we neglected the structure. And in depth 90, you can see there are 2 CH and not 3 CH. So in this case, there should be 1, 2, 3 CH, but we get only 2. So again, from this technique also, we did not, we neglected that structure. And once after recording the depth techniques, we marked all the signals, the ipsocarbon, CH2, CH, CH3, all kinds. So there are 8 quaternary carbons in the compound, 2 CH, 6 CH2, and 1 methyl. Now we took the CH-CoC spectra, and you can see that the quadret, and you have certain multiplex here, and all the signals we assign, and each and every signal now have been marked. So after doing this, we went to the HMBC. Now in HMBC, we saw that the quadret has HMBC with two carbons. So one, it should be this methyl, the CH2 giving HMBC with the CH3 carbon and the oxygen attached carbon. So oxygen attached carbon, it appears at around 160 odd ppm. So this group is there based on the results that we observed here. Based on the HMBC correlations, you can see that this triplet, this quadret, uh, it has this group. The compound has this group. So based on that, we expected such a small, such a moiety in the compound. And then by looking at the aromatic uh, contours here, you can see that one aromatic proton and one aliphatic proton commonly shows HMBC with carbon at around 150 odd ppm. So that means you have a situation like this, wherein this ortho proton shows 1, 2, 3 HMBC with this carbon, and the CH2 aliphatic proton, it has 1, 2, 3. So commonly it shows HMBC. So we predicted this part is there. And then you can see that all the three three aliphatic protons shows HMBC with one particular carbon. So we expected a imine kind of carbon in this at this junction. And so this all these 1, 2, and 3 CH2s shows HMBC with this ipso carbon commonly. So putting it together, we expected this moiety, this fused moiety, and then finally we predicted that it's a pyridine and not the pyran. So we predicted the mechanism, and also the structure was confirmed from the single crystal X-ray. So fortunately, we were able to get more number of crystals. So the compound was, the structure was finally confirmed from the single crystal X-ray. So by this, I think I can stop here now. It has been a long time. So shall I stop?
Yes, sir. Okay, sir.
Yeah, thank you. So I thank Mari College University, the principal Jamal Mohammed College, then Dr. Sheikh Dawood, who is the convener of this uh, webinar, the head of the Department of Physics, Jamal Mohammed College, and I should thank my scholars who have contributed to this by their work. So thank you very much. So maybe I can answer some questions.
Dear participants, do you have any questions? Please share your questions on the chat box. Our resource person will answer your question. Any question from participants?
So maybe they can send the email.
Okay, dear participants, in the absence of questions, I think we can wind up this webinar. We would like to thank our resource person, Dr. Ranjit Kumar, on behalf of Postgraduate and Research Department of Physics, Jamal Ahmed College. We'd also like all the we'd also like to thank all the participants for their patient hearing. If you have any doubts, you can always get our resource person's email ID and you can contact with him. Okay. Thank you, one and all.
Thank you very much, sir.
Dear participants, once again, we meet you tomorrow. Okay. Close my now.
Sir,